Picture this, a spacecraft, millions of miles from Earth, drifting silently through the endless void of space. It's a scene that feels almost poetic, a tiny human-made object against the backdrop of the infinite cosmos. But what if I told you that this spacecraft, the Pioneer 10, wasn't behaving as it should? That somewhere in the vast expanse of the universe, something mysterious was tugging at it, slowing it down in ways that defied everything we thought we knew about physics. This isn't science fiction. It's a real cosmic puzzle that left scientists scratching their heads for decades. Welcome to the mystery of the Pioneer Anomaly, a story that takes us to the edge of our understanding of space, gravity, and the very fabric of the universe. As we dive into this enigma, you'll discover how a tiny, unexpected glitch in the data opened up a world of questions that still linger in the minds of astronomers and physicists today. So, where are you joining us from, and what time is it there? Because tonight, we're embarking on a journey through the stars, unraveling a mystery that reminds us just how much we still have to learn about the cosmos. Stay with us, and by the end of this video, you'll see the universe in a whole new light. Now, let's take a step back and set the stage for this cosmic mystery by exploring the missions that started it all, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these spacecraft were designed to push the boundaries of human exploration, venturing farther into the solar system than any mission before them. Pioneer 10, the first of the pair, was launched in March 1972 with a bold mission to study Jupiter and its moons. Just over a year later, Pioneer 11 followed, aiming not only to explore Jupiter, but also to use the planet's gravity as a slingshot to propel itself toward Saturn. These missions were groundbreaking, marking humanity's first attempts to send probes beyond the asteroid belt and into the outer reaches of our solar system. The objectives of the Pioneer missions were ambitious. They were tasked with gathering data on the gas giants, studying their atmospheres, magnetic fields, and the mysterious radiation belts surrounding them. But beyond their scientific goals, these missions carried a deeper purpose: to test the limits of human ingenuity and technology in the harsh environment of deep space. Each spacecraft was equipped with a suite of instruments designed to measure everything from cosmic rays to solar wind, providing scientists with unprecedented insights into the outer solar system. What made these missions truly remarkable was their longevity. Pioneer 10, for instance, continued to send data back to Earth for over 30 years, far exceeding its original mission timeline. It became the first human-made object to travel beyond the orbit of Pluto, carrying with it a golden plaque designed to communicate with any potential extraterrestrial civilizations that might one day find it. Pioneer 11, though its mission ended earlier, also achieved incredible feats, including the first close-up images of Saturn's rings. These missions were more than just scientific endeavors. They were symbols of humanity's curiosity and determination to explore the unknown. They laid the groundwork for future missions like Voyager and Galileo, proving that we could send spacecraft into the farthest reaches of our solar system and still maintain communication with them. But as we'll soon see, It was during these missions that something unexpected began to happen. A tiny, unexplained deviation in their trajectories that would spark one of the greatest mysteries in modern astrophysics. So, as we reflect on the achievements of Pioneer 10 and 11, it's important to remember that their legacy isn't just about the data that they collected or the planets they explored. It's about the questions they raised, questions that would challenge our understanding of the universe and remind us that even the most carefully planned missions can lead to surprises. And with that, let's turn our attention to the moment when scientists first noticed something was amiss: the discovery of the Pioneer Anomaly. As the Pioneer missions continued their journey through the vastness of space, scientists back on Earth were meticulously tracking their progress. Everything seemed to be going according to plan until it wasn't. It was during the late 1980s that researchers began to notice something peculiar. The spacecraft, which were expected to follow precise trajectories based on the laws of physics, were slowing down ever so slightly. This wasn't just a minor discrepancy, it was a consistent, unexplained deceleration that defied all expectations. At first, the anomaly was so subtle that it could have easily been dismissed as a measurement error or a glitch in the data. But as the years went by, the pattern became undeniable. Both Pioneer 10 and 11 were experiencing the same mysterious drag, as if some unseen force was gently tugging them back. The deceleration was tiny, just a fraction of a nanometer per second squared. But over the vast distances these spacecraft were traveling, even the smallest deviation could add up to something significant. The discovery sent shockwaves through the scientific community. How could two spacecraft, designed and launched with such precision, be slowing down in a way that contradicted the known laws of physics? Initial theories ranged from technical malfunctions to errors in the data collection process. Perhaps the onboard instruments were malfunctioning, or maybe there was an issue with how the signals were being interpreted back on Earth. But as scientists dug deeper, they realized the problem wasn't with the equipment or the data. It was something far more perplexing. The anomaly presented a tantalizing mystery. If it wasn't a technical error, then what could it be? Some researchers began to wonder if there was an unknown force at play, something beyond our current understanding of gravity or the behavior of objects in space. Others speculated that the spacecraft themselves might be the source of the anomaly, perhaps due to their design or the way they interacted with their environment. Whatever the cause, one thing was clear: this wasn't just a minor hiccup in the data. It was a puzzle that would challenge some of the most fundamental principles of physics. As the scientific community grappled with this unexpected discovery, the Pioneer Anomaly became a focal point of intense debate and investigation. It was a reminder that even in the realm of space exploration, where precision and predictability are paramount, the universe still has the power to surprise us. And with that, the stage was set for a new chapter in the story, one where scientists would begin to propose theories, test hypotheses, and search for answers to this cosmic conundrum. As the mystery of the Pioneer Anomaly deepened, scientists began to put forward a range of theories to explain the unexpected behavior of the spacecraft. The first and most straightforward idea was that the anomaly might be the result of a technical error. Perhaps there was a miscalibration in the instruments, or maybe the data being sent back to Earth was being misinterpreted. After all, space missions are incredibly complex, and even the smallest oversight could lead to puzzling results. But as researchers double-checked their calculations and re-examined the data, they found no evidence of such errors. The anomaly persisted, and the search for answers continued. Another early theory focused on the possibility of gravitational influences. Could there be an unknown celestial body, a hidden planet, or a massive object exerting a gravitational pull on the Pioneer spacecraft? This idea was intriguing, as it suggested that our understanding of the solar system might be incomplete. However, detailed observations of the region where the anomaly was detected revealed no such object. The gravitational pull required to explain the deceleration would have been significant, and no evidence of such a massive body was found. This left scientists scratching their heads, wondering if there was another force at play. Some researchers turned their attention to the spacecraft themselves. Could the design or construction of the Pioneer probes be contributing to the anomaly? One hypothesis suggested that heat radiation from the spacecraft's power source, a radioisotope thermoelectric generator, might be causing a tiny but consistent push, effectively slowing the probes down. This idea was particularly interesting because it didn't rely on external forces or unknown objects. Instead, it pointed to the spacecraft's own systems as the source of the mystery. But proving this theory would require detailed analysis and simulations, which would take time and effort. Meanwhile, others began to explore more unconventional ideas. Could the anomaly be evidence of new physics, something beyond our current understanding of gravity and motion? Some scientists speculated that the laws of physics, as we know them, might need to be revised, at least in certain extreme conditions. This was a bold and exciting possibility, but it also raised more questions than answers. If the anomaly was indeed a sign of new physics, what did that mean for our understanding of the universe? And how could such a theory be tested and confirmed? As these theories began to emerge, one thing became clear. The Pioneer anomaly was not just a scientific puzzle, it was a catalyst for curiosity and creativity. Researchers from different fields came together, bringing their unique perspectives and expertise to the table. The anomaly had sparked a wave of intellectual exploration, pushing scientists to think outside the box and challenge long-held assumptions. And while the mystery remained unsolved, the journey to uncover the truth was just beginning. As the search for answers continued, scientists turned their attention to the cosmos itself, wondering if the forces of gravity might hold the key to the Pioneer anomaly. Could there be something out there, something unseen, exerting a gravitational pull on the spacecraft? This line of thinking led researchers to consider the possibility of unknown celestial bodies lurking in the outer reaches of the solar system. Perhaps a hidden planet or a massive object, too faint to detect with current technology, was tugging on the Pioneer probes, causing their unexpected deceleration. The idea was tantalizing, as it suggested that our solar system might still hold secrets waiting to be uncovered. But as astronomers scanned the skies, they found no evidence of such a massive object. The gravitational force required to explain the anomaly would have been significant, and any object capable of producing it should have been detectable. Yet, the observations came up empty. This left scientists with another intriguing possibility: dark matter. This mysterious substance, which makes up a significant portion of the universe's mass, is invisible and doesn't interact with light, making it incredibly difficult to detect. Could dark matter be influencing the Pioneer spacecraft's trajectory? The idea was both exciting and challenging, as it pushed the boundaries of our understanding of the universe. Dark matter's gravitational effects are well documented on a cosmic scale, influencing the motion of galaxies and galaxy clusters. But could it also affect something as small as a spacecraft? Some researchers speculated that if dark matter were unevenly distributed in the solar system, it might create subtle gravitational anomalies. However, this theory faced significant hurdles. For one, the amount of dark matter required to produce the observed deceleration would have to be concentrated in a very specific region, which seemed unlikely. Additionally, the effects of dark matter are typically observed over vast distances, not on the scale of a single spacecraft's journey. Despite these challenges, the dark matter hypothesis sparked a wave of curiosity. It reminded scientists that the universe is full of mysteries, and sometimes the answers lie in the most unexpected places. While the idea didn't provide a definitive explanation for the Pioneer Anomaly, it opened the door to new questions and possibilities. What if dark matter behaves differently than we think? Could there be other, unknown forces at play in the cosmos? These questions kept the scientific community engaged, driving them to explore even more unconventional ideas. As the investigation into gravity's role unfolded, it became clear that the Pioneer Anomaly was more than just a technical glitch or a simple oversight. It was a puzzle that challenged our understanding of the universe itself, and while the answers remained elusive, the journey to uncover them was reshaping the way we think about space, gravity, and the hidden forces that shape our cosmos. As the exploration of gravity's role in the Pioneer Anomaly reached a crossroads, scientists began to shift their focus to a more familiar force: heat. This led to the emergence of the thermal radiation hypothesis, a theory that suggested the spacecraft's own power source might hold the key to the mystery. The idea was both simple and profound. What if the heat generated by the spacecraft systems was influencing its trajectory in ways no one had anticipated? At the heart of this theory was the concept of thermal radiation. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, or RTG, which converted the heat from decaying plutonium into electricity. These generators were essential for keeping the spacecraft operational in the cold depths of space, but they also emitted heat in the form of infrared radiation. This heat wasn't just warming the spacecraft, it was radiating outward into space, creating a tiny but consistent push in the opposite direction. Here's where the physics comes into play. According to the laws of thermodynamics, every action has an equal and opposite reaction. When the RTGs emitted heat, that energy carried momentum. Over time, this momentum could have created a small but steady force, acting against the spacecraft's motion, effectively slowing it down. This phenomenon, known as the recoil effect, might seem negligible at first glance, but over the vast distances traveled by the Pioneer probes, even the tiniest force could accumulate into a measurable deceleration. The thermal radiation hypothesis gained traction because it offered a plausible explanation rooted in well-understood physical principles. Unlike the more speculative ideas involving dark matter or hidden celestial bodies, this theory relied on the spacecraft's own design and behavior. It also aligned with the observed data. The deceleration was consistent and uniform, just as one would expect from a steady source of heat radiation. However, proving this theory wasn't straightforward. The spacecraft's complex design meant that heat wasn't distributed evenly. Some parts of the spacecraft absorbed more heat than others, and the way this heat radiated into space could vary depending on the orientation of the spacecraft. This asymmetry made it difficult to calculate the exact impact of thermal radiation on the spacecraft's trajectory. Scientists had to account for every possible variable, from the shape of the spacecraft to the materials used in its construction. Despite these challenges, the thermal radiation hypothesis marked a turning point in the investigation. It shifted the focus from external forces to the spacecraft itself, highlighting how even the smallest details of engineering could have profound implications in the unforgiving environment of space. As researchers delved deeper into this theory, they began to see the Pioneer Anomaly not just as a mystery to be solved, but as a lesson in the intricate interplay between design, physics, and the vastness of the cosmos. With this new perspective, the scientific community turned to advanced simulations and data analysis to test the thermal radiation hypothesis further, setting the stage for the next chapter in unraveling the Pioneer Anomaly. As the thermal radiation hypothesis gained momentum, scientists knew they had to put it to the test. This meant diving into a world of intricate calculations, simulations, and experiments to determine whether heat was truly the culprit behind the Pioneer Anomaly. The journey to validate this theory was anything but simple, and it required a blend of creativity, precision, and cutting-edge technology. One of the first steps was to create detailed computer models of the Pioneer spacecraft. These models had to account for every aspect of the spacecraft's design, from its asymmetrical shape to the way heat radiated from its radioisotope thermoelectric generators. Researchers painstakingly mapped out how heat flowed through the spacecraft's structure and how it was emitted into space. The goal was to simulate the exact conditions the spacecraft experienced during its journey and see if the thermal radiation could produce the observed deceleration. However, the complexity of the spacecraft's design posed significant challenges. Heat wasn't distributed evenly across the spacecraft, and its orientation in space could change how heat radiated outward. This meant that even small variations in the spacecraft's position could have a big impact on the calculations. To address this, scientists had to run countless simulations, tweaking variables like the spacecraft's angle, the materials used in its construction, and the efficiency of its heat-emitting surfaces. Each simulation brought them closer to understanding whether thermal radiation could explain the anomaly, but it also highlighted just how delicate and precise these calculations needed to be. Another hurdle was the sheer distance of the Pioneer spacecraft from Earth. By the time scientists began testing the thermal hypothesis, the spacecraft were billions of miles away, making it nearly impossible to gather new data directly from them. Instead, researchers had to rely on decades-old telemetry data, which provided limited information about the spacecraft's behavior. This meant that every calculation had to be cross-checked and validated multiple times to ensure accuracy. Even the smallest error in interpreting the data could lead to incorrect conclusions, so the margin for error was razor thin. Despite these challenges, the results of the simulations began to paint a compelling picture. The models showed that thermal radiation could indeed produce a small but consistent force acting against the spacecraft's motion. Over time, this force could accumulate into the deceleration observed by scientists. The data aligned remarkably well with the predictions of the thermal radiation hypothesis, giving researchers confidence that they were on the right track. But the work didn't stop there. To further validate the theory, scientists turned to real-world experiments. They studied how heat radiation behaves in controlled environments, using scaled-down models of the spacecraft to observe the effects of thermal recoil. These experiments provided additional evidence that heat radiation could influence the motion of an object in space, even if the force was incredibly small. Combined with the simulations, these findings strengthened the case for the thermal radiation hypothesis, bringing scientists one step closer to solving the mystery. As the evidence mounted, the scientific community began to see the Pioneer Anomaly in a new light. What had once seemed like an unsolvable puzzle was now revealing itself as a fascinating interplay of physics, engineering, and the harsh realities of space travel. The journey to test the thermal hypothesis wasn't just about solving a mystery. It was a testament to the power of curiosity, collaboration, and the relentless pursuit of knowledge. And with each new discovery, the story of the Pioneer Anomaly became not just a tale of unexplained behavior, but a lesson in how even the smallest details can shape our understanding of the universe. As the investigation into the Pioneer Anomaly deepened, attention turned to the spacecraft itself, its design, materials, and how these elements might have played a role in the mysterious deceleration. The Pioneer spacecraft were marvels of engineering, built to withstand the harsh conditions of space, but their very design may have held the key to understanding the anomaly. One of the most striking features of the Pioneer spacecraft was their asymmetrical shape. Unlike many modern spacecraft, which are designed to be as symmetrical as possible to ensure stability, the Pioneers had a unique, lopsided structure. This asymmetry wasn't just a quirk of design, it had real consequences for how heat was distributed and radiated into space. The spacecraft's radioisotope thermoelectric generators, which provided power, were mounted on long booms that extended outward from the main body. This arrangement created an uneven distribution of heat, with more heat radiating from one side of the spacecraft than the other. Over time, this imbalance could have produced a tiny but consistent force, nudging the spacecraft off course. The materials used in the spacecraft's construction also played a crucial role. The Pioneers were built with a combination of metals and insulating materials that were chosen for their durability and ability to withstand extreme temperatures. However, these materials also influenced how heat was absorbed, retained, and emitted. For example, the reflective surfaces on the spacecraft were designed to protect sensitive instruments from the sun's heat, but they also affected how heat radiated into space. Even small differences in the way these materials interacted with heat could have contributed to the anomaly. Another factor was the spacecraft's orientation in space. As the Pioneers traveled farther from the sun, their orientation changed, altering how heat was emitted. This meant that the force produced by thermal radiation wasn't constant. It varied depending on the spacecraft's position and angle. Scientists had to account for these variations in their calculations, adding another layer of complexity to the investigation. The interplay between the spacecraft's design, materials, and orientation created a delicate balance that, when disrupted, could lead to unexpected behavior. The role of spacecraft design in the Pioneer Anomaly highlights how even the smallest details can have far-reaching consequences. What might have seemed like minor design choices at the time, like the placement of a heat source or the choice of materials, turned out to be critical factors in solving one of space exploration's greatest mysteries. This realization not only shed light on the anomaly, but also provided valuable lessons for future spacecraft design. Engineers and scientists began to rethink how they approached the challenges of heat management and symmetry, ensuring that future missions would avoid similar pitfalls. As the story of the Pioneer Anomaly unfolded, it became clear that the spacecraft themselves were more than just tools for exploration. They were intricate systems where every component played a part in the larger mission. The lessons learned from their design continue to shape the way we build and launch spacecraft, reminding us that even the smallest details can have a big impact on our journey through the cosmos. As the investigation into the Pioneer Anomaly progressed, another layer of complexity emerged: the challenges of collecting and interpreting data from spacecraft billions of miles away. Imagine trying to solve a puzzle where the pieces are scattered across the vastness of space, and every piece takes hours or even days to reach you. This was the reality for scientists studying the Pioneers. One of the biggest hurdles was the sheer distance between Earth and the spacecraft. By the time the anomaly was detected, Pioneer 10 and Pioneer 11 were already far beyond the orbit of Pluto, traveling deeper into interstellar space. This immense distance meant that signals sent from Earth took hours to reach the spacecraft, and the data they sent back took just as long to return. Every piece of information scientists received was a snapshot of the past, making real-time analysis impossible. This delay forced researchers to work with outdated data, adding a layer of uncertainty to their calculations. Communication with the spacecraft was also limited. The Pioneers were equipped with relatively simple radio systems, designed to transmit basic telemetry data, information about their speed, position, and health. While this was sufficient for their original mission, it posed a challenge when scientists needed more detailed data to understand the anomaly. The spacecraft couldn't send back high-resolution measurements or real-time updates. leaving researchers to piece together the puzzle with incomplete information. Another issue was the weakening signal strength. As the pioneers traveled farther from Earth, the radio signals they sent back became fainter and harder to detect, requiring increasingly sensitive equipment on the ground to pick them up. Even with the most advanced antennas, there were moments when the signal was so weak that it was nearly lost in the background noise of space. This made it difficult to gather consistent, reliable data, and scientists often had to rely on intermittent readings to draw their conclusions. Interpreting the data was no less challenging. The pioneers were designed to operate in the relatively predictable environment of the solar system, but as they ventured into uncharted territory, unexpected factors came into play. Cosmic radiation, solar wind, and even the gravitational pull of distant stars could subtly influence the spacecraft's trajectory, complicating the analysis. Scientists had to account for these variables while trying to isolate the effects of the anomaly, a task that required both precision and creativity. Despite these obstacles, the scientific community persevered. They developed new techniques to enhance the quality of the data they received, using advanced algorithms to filter out noise and improve signal clarity. They also revisited old data, applying modern analytical tools to uncover patterns that might have been missed decades earlier. This painstaking process of data collection and interpretation was a testament to the dedication and ingenuity of the researchers involved. The challenges of working with data from the pioneers underscored the importance of patience and precision in scientific exploration. It reminded us that even in the age of advanced technology, some mysteries require time, effort, and a willingness to embrace uncertainty. As we continue to explore the cosmos, the lessons learned from the Pioneer Anomaly serve as a reminder that every piece of data, no matter how small or delayed, brings us one step closer to understanding the universe. As the investigation deepened, scientists began to explore whether external forces beyond the spacecraft itself could be influencing its unexpected behavior. This led them to consider the vast and dynamic environment of space, where countless factors could subtly alter the Pioneer's trajectory. One of the first possibilities they examined was the impact of solar wind, a stream of charged particles constantly emitted by the sun. While solar wind is typically weak, its cumulative effect over time could potentially nudge a spacecraft off course, especially one traveling as far and as long as the Pioneers. Researchers analyzed whether this constant flow of particles might have contributed to the anomaly, but the calculations showed that solar wind alone couldn't fully explain the observed deceleration. Another external factor under scrutiny was cosmic dust, tiny particles scattered throughout space. Though individually insignificant, these particles could collectively exert a drag force on the spacecraft as it moved through the interstellar medium. Scientists theorized that the Pioneers, traveling at high speeds, might be colliding with enough dust to create a measurable slowdown. However, measurements of the density of cosmic dust in the regions the spacecraft passed through suggested that this effect was too small to account for the anomaly. While cosmic dust played a role, it wasn't the primary culprit. The gravitational influence of distant celestial bodies also came into question. Could the pull of unseen objects, like rogue planets or small asteroids, be tugging on the pioneers, while gravity from massive objects like planets and stars is well understood? The possibility of smaller, undetected bodies exerting a subtle influence couldn't be ruled out entirely. Yet, detailed calculations and observations of the spacecraft's path revealed no significant gravitational anomalies that matched the pattern of the deceleration. This left scientists with more questions than answers, pushing them to consider even more unconventional explanations. One intriguing idea was the potential effect of dark matter, a mysterious substance that makes up a significant portion of the universe's mass but doesn't interact with light. Could dark matter be exerting a gravitational force on the pioneers, causing their unexpected slowdown? While this theory captured the imagination of many, it remains speculative. Dark matter's properties are still poorly understood, and without direct evidence of its interaction with the spacecraft, this explanation remained on the fringes of scientific debate. As researchers continued to explore these external influences, they faced a recurring challenge: isolating the effects of the anomaly from the countless variables at play in the vastness of space. Each potential factor, solar wind, cosmic dust, gravitational forces, and even dark matter, added a layer of complexity to the puzzle, yet none provided a definitive answer. This phase of the investigation highlighted the intricate balance between known and unknown forces in the cosmos, reminding us that space is far from empty. It's a dynamic environment where even the smallest influences can ripple across vast distances, shaping the journey of spacecraft like the pioneers in ways we're still striving to understand. With external factors unable to fully explain the anomaly, the focus began to shift back to the spacecraft itself, setting the stage for a deeper examination of its design and internal mechanisms. As the search for answers continued, the spotlight turned to one of the most enigmatic substances in the universe: dark matter. This mysterious material, invisible to our telescopes and undetectable by conventional means, makes up a staggering portion of the cosmos. In fact, scientists estimate that dark matter accounts for roughly 85% of all matter in the universe. Yet, despite its prevalence, it remains one of the greatest unsolved mysteries in modern physics. The idea that dark matter could be influencing the Pioneer spacecraft was both tantalizing and perplexing. Could this unseen force be tugging on the pioneers, causing their unexpected deceleration? Dark matter doesn't interact with light, making it invisible to our eyes and instruments. It doesn't emit, absorb, or reflect any form of electromagnetic radiation, which is why it's so difficult to detect. However, its presence is inferred through its gravitational effects. Galaxies, for instance, rotate at speeds that would tear them apart, if not for the gravitational pull of dark matter holding them together. This invisible scaffolding shapes the structure of the universe on the largest scales, from galaxy clusters to the cosmic web itself. Given its profound influence, it wasn't far-fetched to consider whether dark matter might also be affecting the pioneers. The theory proposed that as the spacecraft traveled through space, they might be passing through regions with higher concentrations of dark matter. If this were the case, the gravitational pull of these invisible particles could subtly alter the Pioneer's trajectory, causing the observed slowdown. It was an elegant explanation, one that tied the anomaly to a fundamental aspect of the universe's composition. But there was a catch. Dark matter's properties are still largely unknown. While its gravitational effects are undeniable, its distribution and density in the regions traversed by the pioneers remain speculative. Scientists faced a significant challenge in testing this hypothesis. Without direct evidence of dark matter's interaction with the spacecraft, they had to rely on indirect methods. They analyzed the Pioneer's trajectory, searching for patterns that might align with the expected gravitational influence of dark matter. They also studied the distribution of dark matter in the Milky Way, using computer simulations to model how it might affect objects moving through space. Yet, the results were inconclusive. While dark matter remained a compelling possibility, the lack of concrete evidence meant it couldn't be confirmed as the primary cause of the anomaly. This exploration into dark matter highlighted the broader challenges of studying the unseen forces that shape our universe. It underscored the limits of our current understanding and the need for new tools and technologies to probe these mysteries further. While the dark matter connection didn't provide a definitive answer to the Pioneer anomaly, it opened the door to deeper questions about the nature of the cosmos. What other invisible forces might be at play? How do they influence the objects we send into space? And what might we discover as we continue to push the boundaries of our knowledge? As the investigation into dark matter reached its limits, the focus began to shift once again, this time toward the spacecraft's own design and the possibility that the answer lay closer to home. As the search for answers continued, scientists began to explore ideas that ventured beyond the boundaries of conventional physics. One such avenue was the possibility that the Pioneer anomaly might be pointing to a need to rethink some of the fundamental laws of the universe. This led to the emergence of alternative physics theories, including modifications to Einstein's theory of relativity, which had long been the cornerstone of our understanding of gravity and motion. Einstein's theory of general relativity has been incredibly successful in explaining the behavior of massive objects, from the bending of light around stars to the orbits of planets. However, some scientists wondered if the Pioneer anomaly could be a sign that relativity needed to be tweaked, especially when applied to the vast distances and extreme conditions of deep space. One proposal suggested that the laws of gravity might behave differently on cosmic scales, leading to subtle deviations in the motion of spacecraft like the Pioneers. This idea, known as modified Newtonian dynamics, or MND, had already been proposed to explain certain discrepancies in the rotation of galaxies. Could it also account for the Pioneer's unexpected deceleration? Another intriguing theory involved the concept of extra dimensions. Some physicists speculated that the universe might have more than the three spatial dimensions we experience in everyday life. These hidden dimensions, if they existed, could influence the behavior of gravity in ways that might explain the anomaly. For instance, gravity could leak into these extra dimensions, causing it to weaken slightly over vast distances. This weakening could then result in the observed slowdown of the Pioneers. While this idea was highly speculative, It opened up fascinating possibilities for reimagining the fabric of space and time. Yet another line of thought focused on the idea of variable physical constants. In physics, certain values, like the speed of light or the gravitational constant, are considered unchanging. But what if these constants weren't so constant after all? Some researchers propose that the gravitational constant might vary slightly over time or across different regions of space. If true, this could lead to subtle changes in the way gravity affects objects like the Pioneers, potentially explaining the anomaly. These unconventional theories, while bold and imaginative, faced significant challenges. They required not only new mathematical frameworks, but also experimental evidence to support them. Testing these ideas was no small feat, as they often involved phenomena that were difficult to observe or measure directly. Despite these hurdles, the exploration of alternative physics theories highlighted the willingness of scientists to question established ideas and push the boundaries of knowledge. It also underscored the complexity of the Pioneer Anomaly, which resisted easy explanations and continued to inspire creative thinking. As the scientific community grappled with these unconventional ideas, another possibility began to gain traction: that the answer might lie not in the mysteries of the cosmos, but in the very design of the spacecraft themselves. This shift in focus would lead researchers to examine the Pioneer's construction and the role of thermal radiation, a theory that would eventually bring them closer to solving the puzzle. As the theories multiplied, the scientific community found itself in the midst of a spirited debate. The Pioneer Anomaly wasn't just a puzzle, it was a battleground of ideas, where established principles clashed with bold new hypotheses. Scientists from around the world brought their expertise to the table, each offering their own perspective on what might be causing the spacecraft's unexpected behavior. This wasn't just about solving a mystery, it was about defending or challenging the very foundations of physics. On one side were those who believed the anomaly could be explained within the framework of existing science. They argued that the answer likely lay in overlooked details, perhaps a miscalculation in the spacecraft's trajectory, or an unaccounted for force like thermal radiation. These researchers emphasized the importance of double-checking data and refining models before jumping to conclusions. For them, the anomaly was a reminder of how complex and unpredictable space exploration could be, but not necessarily a reason to rewrite the laws of physics. On the other side were the proponents of more radical ideas. They saw the anomaly as a potential crack in the edifice of modern physics, a hint that our understanding of the universe might be incomplete. Theories like modified gravity, extra dimensions, and variable physical constants were met with both excitement and skepticism. While some scientists welcomed these ideas as a breath of fresh air, others dismissed them as speculative or premature. The debates were intense, with researchers presenting their arguments at conferences, in journals, and even in spirited online discussions. What made these debates so fascinating was the blend of collaboration and competition. Scientists worked together to analyze data, share insights, and test hypotheses, but they also competed to be the first to crack the mystery. This dynamic drove the field forward, pushing researchers to think creatively and rigorously. It also highlighted the human side of science, the passion, the egos, and the occasional clashes that come with pursuing groundbreaking discoveries. Amid the disagreements, one thing was clear: the Pioneer Anomaly had captured the imagination of the scientific community. It wasn't just a technical problem to be solved. It was a challenge that forced scientists to question their assumptions and explore new frontiers of knowledge. And as the debates raged on, one question loomed large: would the answer come from rethinking the cosmos or from re-examining the spacecraft itself? This question would soon lead researchers down a path that brought them closer to the truth. As the debates continued to unfold, scientists turned to a powerful tool to help unravel the mystery: computer simulations. These advanced models became a crucial part of the investigation, allowing researchers to recreate the conditions of the Pioneer spacecraft's journey and test their theories in a virtual environment. By feeding data into these simulations, scientists could observe how different factors like thermal radiation, gravitational forces, or even hypothetical new physics might influence the spacecraft's trajectory. This approach offered a way to explore possibilities that were impossible to test in real time, given the vast distances and limitations of space communication. One of the key challenges was ensuring the accuracy of these simulations. Researchers had to account for every conceivable variable, from the spacecraft's design and materials to the subtle effects of solar radiation and cosmic dust. Even the smallest oversight could lead to misleading results, so teams worked meticulously to refine their models. They cross-checked their findings with real-world data from the Pioneer missions, ensuring that their simulations aligned with the observed behavior of the spacecraft. This painstaking process highlighted the importance of precision in scientific inquiry, as even the tiniest error could derail the search for answers. The simulations also allowed scientists to explore more radical ideas without the constraints of traditional experimentation. For instance, some researchers used these models to test theories involving modified gravity or the influence of dark matter. While these ideas were speculative, the simulations provided a way to assess their plausibility. If a particular hypothesis consistently produced results that matched the anomaly, it could be considered a potential explanation. On the other hand, if the simulations failed to replicate the observed behavior, the theory could be set aside, at least temporarily. What made these computer models so valuable was their ability to bring clarity to a complex problem. By isolating specific variables and testing them one by one, researchers could narrow down the list of possible explanations. This methodical approach helped shift the focus from broad speculation to targeted investigation, bringing the scientific community closer to a resolution. It also demonstrated the power of technology in modern science, showing how tools like computer simulations could bridge the gap between theory and reality. As the simulations progressed, one hypothesis began to stand out: the thermal radiation theory. The models suggested that heat emitted by the spacecraft's power source could indeed produce the observed deceleration. This finding didn't just solve the mystery, it also underscored the importance of considering even the most mundane factors in scientific research. Sometimes, the answer lies not in the stars, but in the details closer to home. With this breakthrough, the focus shifted to gathering more evidence to confirm the thermal hypothesis, setting the stage for the next chapter in the story of the Pioneer Anomaly. As the scientific community worked tirelessly to solve the Pioneer Anomaly, the mystery began to capture the imagination of the wider world. The idea of a spacecraft behaving in ways that defied explanation sparked curiosity and wonder, making its way into popular culture. Books, movies, and documentaries started to explore the anomaly, often weaving it into larger narratives about the mysteries of the universe. For many, the Pioneer Anomaly became a symbol of the unknown, a reminder that even in an age of advanced technology, space still holds secrets waiting to be uncovered. Science fiction authors, in particular, found inspiration in the anomaly. Stories began to emerge, imagining scenarios where the unexplained deceleration was caused by alien technology, hidden dimensions, or even time travel. These tales often use the anomaly as a jumping-off point to explore deeper questions about humanity's place in the cosmos. While these ideas were purely speculative, they resonated with audiences, tapping into a universal fascination with the unknown. The Pioneer Anomaly became a plot device that allowed writers to blend hard science with imaginative storytelling, creating works that were both entertaining and thought-provoking. Documentaries also played a significant role in bringing the anomaly to the public's attention. Programs dedicated to space exploration often featured segments on the Pioneer missions, highlighting the anomaly as one of the great unsolved mysteries of modern science. These documentaries not only educated viewers about the technical aspects of the anomaly, but also emphasized its broader implications. They asked questions like, what does it mean for our understanding of physics? Could there be forces or phenomena in the universe that we have yet to discover? By framing the anomaly in this way, these programs help to spark a sense of wonder and curiosity in audiences, encouraging them to think more deeply about the cosmos. Even mainstream movies and television shows began to reference the anomaly, though often in a more dramatized form. While these portrayals took creative liberties, they still contributed to the anomaly's cultural impact. For many viewers, these references served as an introduction to the real-life mystery, prompting them to learn more about the science behind it. In this way, popular culture helped to bridge the gap between scientific inquiry and public interest, making complex ideas more accessible to a broader audience. The Pioneer Anomaly also influenced the way space exploration was portrayed in media. It became a reminder that even the most carefully planned missions could encounter the unexpected, adding an element of unpredictability to stories about space travel. This shift in narrative reflected a growing awareness of the challenges and uncertainties inherent in exploring the cosmos. It also highlighted the importance of curiosity and perseverance, qualities that are essential not just for scientists, but for anyone seeking to push the boundaries of knowledge. As the anomaly continued to capture the public's imagination, it also inspired a new generation of scientists and engineers. For many, the mystery served as a reminder of why they were drawn to space exploration in the first place. The thrill of discovery, the joy of solving puzzles, and the desire to understand the universe on a deeper level. In this way, the Pioneer Anomaly became more than just a scientific puzzle. It became a symbol of the enduring human spirit of exploration. With its blend of mystery, science, and imagination, the Pioneer Anomaly left a lasting mark on popular culture. It reminded us that the universe is full of surprises, and that even the smallest anomaly can lead to profound questions. As we continue to explore the cosmos, stories like the Pioneer Anomaly will always have a place in our collective imagination, inspiring us to look to the stars and wonder what else might be out there. As the years passed and the mystery of the Pioneer Anomaly persisted, a turning point finally arrived. Scientists began to shift their focus toward a more grounded explanation: the thermal radiation hypothesis. This idea suggested that the spacecraft's own heat emissions could be the key to understanding its unexpected deceleration. It was a moment of clarity, a breakthrough that brought the scientific community closer to solving the puzzle. The thermal radiation hypothesis proposed that the heat generated by the spacecraft's power source, its radioisotope thermoelectric generators, was being emitted unevenly. This uneven distribution of heat could create a tiny but consistent force, pushing against the spacecraft and causing it to slow down ever so slightly. At first, this idea seemed almost too simple, but as researchers dug deeper, they realized it might hold the answer they had been searching for. To test this theory, scientists turned to detailed computer simulations and mathematical models. They meticulously analyzed the spacecraft's design, paying close attention to how heat was distributed across its surface. What they discovered was fascinating. The Pioneer spacecraft's asymmetrical shape meant that heat wasn't radiating evenly in all directions. Instead, more heat was being emitted from certain parts of the spacecraft, creating a subtle but measurable force that acted like a gentle brake. This breakthrough didn't come easily. It required revisiting decades-old data and applying modern analytical techniques to uncover patterns that had been overlooked before. Researchers had to account for every possible variable, from the spacecraft's materials to its orientation in space. But as the evidence mounted, the thermal radiation hypothesis began to gain traction, offering a plausible explanation that didn't require invoking unknown forces or exotic physics. The moment this hypothesis started to take hold was a pivotal one for the scientific community. It marked a shift from speculation to a more concrete understanding of the anomaly. While the idea of heat causing the deceleration might not have been as thrilling as some of the more imaginative theories, it was a reminder that sometimes the simplest explanations are the most powerful. This breakthrough also highlighted the importance of persistence and collaboration in science, as it took years of collective effort to piece together the evidence. As the thermal radiation hypothesis gained acceptance, it opened the door to new questions and avenues of research. Scientists began to explore how this discovery could influence future spacecraft design, ensuring that similar anomalies could be avoided. It also underscored the importance of considering even the smallest details when planning missions, as something as seemingly insignificant as heat distribution could have a profound impact on a spacecraft's trajectory. This breakthrough moment wasn't just about solving a mystery. It was a testament to the power of curiosity and the scientific method. It showed that even the most perplexing problems can be unraveled with patience creativity, and a willingness to question assumptions. And as the thermal radiation hypothesis took center stage, it brought the Pioneer Anomaly one step closer to being fully understood, reminding us that the universe often reveals its secrets in the most unexpected ways. As the thermal radiation hypothesis began to take shape, scientists realized that solving the Pioneer Anomaly would require more than just new ideas. It would demand a fresh look at old data. Decades had passed since the Pioneer spacecraft had sent their final signals, but the information they had transmitted was far from obsolete. Hidden within those streams of data were clues that, with the help of modern technology, could finally shed light on the mystery. Researchers turned their attention to the vast archives of information collected during the Pioneer missions. This wasn't just a matter of dusting off old files. It was a meticulous process of reanalyzing every piece of data with tools and techniques that hadn't existed when the spacecraft were first launched. Advanced computer algorithms, capable of processing enormous amounts of information, allowed scientists to sift through the data with unprecedented precision. They were looking for patterns, anomalies, and subtle details that might have been overlooked in the past. One of the biggest challenges was accounting for the limitations of the original data collection methods. The Pioneer spacecraft were designed in the 1970s, and their instruments were far less sophisticated than those used today. Signals from deep space were faint and often noisy, making it difficult to extract clear information. But modern technology offered a solution. By applying advanced signal processing techniques, researchers were able to clean up the data, removing interference and enhancing the quality of the original measurements. As they dug deeper, scientists began to uncover new insights. They revisited the spacecraft's trajectory data, recalculating its position and velocity with greater accuracy. They also analyzed the thermal properties of the spacecraft in more detail, using updated models to simulate how heat was distributed across its surface. These simulations revealed that the uneven emission of heat wasn't just a minor factor. It was a consistent force that aligned perfectly with the observed deceleration. This process of revisiting old data wasn't just about confirming the thermal radiation hypothesis. It was also about learning from the past. By studying the Pioneer missions with fresh eyes, researchers gained a deeper understanding of how spacecraft behave in deep space. They discovered that even small design choices, like the placement of heat sources or the materials used, could have significant effects on a mission's outcome. These lessons would prove invaluable for future spacecraft, helping engineers avoid similar anomalies. The effort to reanalyze decades-old data was a testament to the enduring value of scientific exploration. It showed that even information collected long ago could hold the key to solving modern mysteries, provided we have the tools and the curiosity to look for it. And as the pieces of the puzzle began to fall into place, the Pioneer Anomaly moved closer to being fully understood, reminding us that the pursuit of knowledge is a journey that never truly ends. As the pieces of the puzzle came together, the scientific community reached a turning point. The mystery of the Pioneer Anomaly, which had baffled researchers for decades, finally had a clear and widely accepted explanation. At the heart of it all was thermal radiation, a subtle but powerful force that had been quietly influencing the spacecraft's journey through space. The breakthrough came when scientists realized that the heat generated by the spacecraft's power source wasn't just escaping into space uniformly. Instead, it was being emitted unevenly, with more heat radiating from certain parts of the spacecraft than others. This uneven distribution created a tiny but consistent push, acting like a gentle but persistent force that slowed the spacecraft down over time. It was this thermal recoil force that matched the observed deceleration almost perfectly. To put it simply, the spacecraft's own heat was nudging it off course. This might sound surprising, but in the vacuum of space, even the smallest forces can have a significant impact over long distances. The Pioneer spacecraft, with their asymmetrical design and heat-emitting components, were particularly susceptible to this effect. Modern simulations and recalculations confirmed that this thermal radiation was the primary cause of the anomaly, aligning with the data collected over the years. What made this explanation so compelling was its simplicity. It didn't require exotic physics or unseen forces, just a careful understanding of how heat behaves in space. This revelation not only solved the mystery, but also highlighted the importance of considering even the smallest details in spacecraft design. Engineers and scientists learned that something as seemingly insignificant as heat distribution could have far-reaching consequences for a mission's success. The resolution of the Pioneer Anomaly was a triumph of persistence and ingenuity. It showed how revisiting old data with new tools could unlock answers that had once seemed out of reach. And while the mystery was solved, it left behind a valuable lesson. In the vast and unpredictable expanse of space, even the most familiar forces can surprise us. This discovery not only closed a chapter in space exploration, but also opened the door to new possibilities, reminding us that every mystery solved brings us one step closer to understanding the universe. The resolution of the Pioneer Anomaly wasn't just the end of a mystery, it was the beginning of a new way of thinking about space exploration. One of the most important lessons from this decades-long puzzle was the critical role of spacecraft design. The anomaly revealed how even the smallest details, like the way heat is distributed across a spacecraft, can have profound effects on its trajectory. Engineers learned that asymmetrical designs, while sometimes necessary for functionality, could introduce unintended forces that alter a mission's course. This insight has since influenced the design of modern spacecraft, with greater attention paid to balancing heat distribution and minimizing any potential recoil effects. Another key takeaway was the importance of meticulous data analysis. The Pioneer Anomaly showed that sometimes the answers we seek are hidden in the data we already have, waiting for the right tools and perspectives to uncover them. Scientists spent years revisiting old data, applying new technologies, and refining their models to finally crack the case. This process underscored the value of patience and persistence in scientific research, as well as the need to continually question and reevaluate our assumptions. What seemed like an unsolvable mystery at first became a testament to the power of curiosity and innovation. Perhaps the most profound lesson was the reminder that in science, No detail is too small to matter. The anomaly taught us to look beyond the obvious and consider even the most subtle forces at play. It also highlighted the importance of collaboration across disciplines, as solving the mystery required expertise in physics, engineering, and data analysis. This interdisciplinary approach has since become a cornerstone of modern space exploration, ensuring that future missions are better equipped to handle the complexities of the cosmos. The Pioneer Anomaly also reinforced the idea that science is a journey of discovery, not just a search for answers. It reminded us that every mystery, no matter how perplexing, is an opportunity to learn and grow. By embracing uncertainty and challenging our assumptions, we open the door to new possibilities and deeper understanding. The lessons from the Pioneer missions continue to shape the way we explore space, proving that even the smallest anomalies can lead to the biggest breakthroughs. And as we look to the future, these lessons will guide us as we venture further into the unknown, ready to uncover the next great mystery of the universe. As we reflect on the journey of the Pioneer missions, it's impossible to overlook the profound legacy they've left behind. Pioneer 10 and Pioneer 11 were more than just spacecraft. They were trailblazers, venturing into uncharted territory and paving the way for future exploration. These missions didn't just gather data, they expanded our understanding of the solar system in ways that continue to resonate today. From their groundbreaking flybys of Jupiter and Saturn to their role in mapping the outer reaches of our cosmic neighborhood, the pioneers redefined what we thought was possible. One of their most significant contributions was the wealth of information they provided about the gas giants. Pioneer 10 became the first spacecraft to travel through the asteroid belt and make a close approach to Jupiter, capturing stunning images and revealing details about the planet's atmosphere, magnetic field, and radiation belts. Pioneer 11 followed suit, not only studying Jupiter, but also becoming the first to explore Saturn, sending back data that would shape our understanding of its rings and moons. These discoveries laid the groundwork for future missions, like Voyager and Cassini, which built on the Pioneer's findings to deepen our knowledge of these distant worlds. But the legacy of Pioneer 10 and 11 extends beyond their scientific achievements. These missions demonstrated the power of human ingenuity and determination. At a time when space exploration was still in its infancy, the pioneers proved that we could send spacecraft across vast distances and gather invaluable information about our solar system. They inspired a generation of scientists, engineers, and dreamers, showing us that the cosmos was within our reach. Even the anomaly, which once seemed like a stumbling block, became part of their enduring story. It reminded us that exploration is as much about the questions we ask as the answers we find. The lessons learned from the pioneers' unexpected behavior have influenced the design of every spacecraft that followed, ensuring that future missions are more precise, resilient, and capable of handling the complexities of space. Today, as we look back on the pioneers' journey, we're reminded of how far we've come and how much further we have to go. These missions didn't just explore the solar system, they ignited a spark of curiosity that continues to drive us forward. They showed us that even in the face of uncertainty, there's always something new to discover. And as we venture deeper into the cosmos, The legacy of Pioneer 10 and 11 will always remind us of the courage, creativity, and curiosity that make exploration possible. As we turn our gaze toward the future, the lessons learned from the Pioneer Anomaly have become a cornerstone in the evolution of spacecraft design. This unexpected behavior, once a source of confusion, has now transformed into a blueprint for innovation. Modern spacecraft are built with a deeper understanding of the subtle forces that can influence their trajectories, ensuring they are more precise and reliable than ever before. One of the most significant changes inspired by the anomaly is the meticulous attention to thermal management. Engineers now carefully account for the heat generated by a spacecraft's power systems, ensuring that thermal radiation doesn't create unintended thrust or deceleration. This level of precision wasn't just a reaction to the Pioneer's experience. It became a proactive measure integrated into the design process from the very beginning. By simulating and testing thermal effects in advance, scientists can predict and mitigate potential anomalies before a spacecraft even leaves the ground. Another critical advancement lies in the way spacecraft are shaped and balanced. The Pioneer's asymmetrical design, which contributed to their unexpected behavior, has led to a greater emphasis on symmetry and stability in modern missions. Spacecraft are now engineered to distribute mass and heat more evenly, reducing the risk of unpredictable movements. This shift has not only improved accuracy, but also extended the lifespan of missions, allowing them to gather data for longer periods without deviation. Communication and data collection have also seen remarkable improvements. The challenges faced by the Pioneers, with their limited signals and delayed transmissions, have driven the development of more robust communication systems. Modern spacecraft are equipped with advanced antennas and data processing tools, enabling real-time monitoring and adjustments. This means that if an anomaly does arise, scientists can respond quickly, minimizing its impact on the mission. Perhaps the most profound legacy of the Pioneer Anomaly is the mindset it instilled in the space exploration community. It taught us to expect the unexpected and to design with flexibility in mind. Today's spacecraft are built to adapt, with systems that can be reprogrammed or reconfigured even after launch. This adaptability ensures that missions can continue to achieve their goals, even in the face of unforeseen challenges. As we look ahead, the lessons from the Pioneers continue to guide us. Each new mission builds on their legacy, pushing the boundaries of what's possible while honoring the curiosity and determination that drove those early explorations. The future of spacecraft design is not just about reaching further into the cosmos, it's about doing so with greater precision, resilience, and a deeper understanding of the forces that shape our journey. And as we venture into the unknown, we carry with us the spirit of those trailblazing missions, reminding us that every anomaly is an opportunity to learn, grow, and explore. Even as we celebrate the strides made in understanding the Pioneer Anomaly, there remain intriguing questions that continue to spark curiosity and debate. While the thermal radiation hypothesis has provided a compelling explanation, some aspects of the anomaly still leave room for wonder. For instance, could there have been other, less obvious forces at play that we haven't fully accounted for. The universe is vast and filled with phenomena we are only beginning to comprehend, and the pioneer's journey reminds us that even the most carefully studied events can hold hidden layers of complexity. One lingering question revolves around the precision of our measurements. While modern technology has allowed us to revisit and analyze the pioneer's data with greater accuracy, could there still be subtle errors or overlooked factors in the original observations? Space is a dynamic environment, and even the smallest variables like the influence of cosmic dust or fluctuations in solar wind might have played a role in ways we haven't fully understood. These uncertainties keep the door open for further exploration and refinement of our theories. Another area of interest is the potential role of dark matter. While the thermal radiation hypothesis has largely explained the anomaly, some scientists wonder if dark matter, a mysterious substance that makes up a significant portion of the universe, could have contributed to the pioneer's unexpected behavior. Though this idea remains speculative, it highlights how the anomaly continues to inspire new lines of inquiry, pushing us to explore the boundaries of our knowledge. The pioneer's journey also raises broader questions about the nature of space itself. Are there other, yet to be discovered forces or interactions that could affect spacecraft in ways we can't yet predict? The anomaly serves as a reminder that our understanding of the cosmos is still evolving, and every mystery we solve often leads to new ones waiting to be unraveled. As we reflect on these unanswered questions, the Pioneer Anomaly stands as a testament to the enduring allure of space exploration. It reminds us that even in an age of advanced technology and scientific breakthroughs, the universe still holds secrets that challenge our assumptions and ignite our imaginations. And as we continue to probe the depths of space, these mysteries serve as beacons, guiding us toward new discoveries and a deeper understanding of the cosmos. As we delve deeper into the story of the Pioneer Anomaly, it's worth taking a moment to recognize the unsung heroes who played a crucial role in unraveling this cosmic mystery: citizen scientists. While professional researchers led the charge, the contributions of amateur astronomers and space enthusiasts around the world added a unique dimension to the investigation. Their collective curiosity and dedication remind us that science is not just the domain of experts, it's a shared endeavor that thrives on collaboration and passion. One of the most remarkable aspects of the Pioneer Anomaly investigation was how it captured the imagination of people outside traditional scientific circles. Amateur astronomers, armed with telescopes and a love for the cosmos, began tracking the spacecraft's movements and sharing their observations online. These enthusiasts often brought fresh perspectives and creative ideas to the table, challenging researchers to think outside the box. In some cases, their meticulous data collection even helped fill gaps in the official records, providing valuable insights that might have otherwise been overlooked. The rise of online platforms and open source tools further amplified the role of citizen scientists. Forums and collaborative projects allowed amateurs to connect with professionals, exchanging ideas and refining theories. This open exchange of knowledge not only accelerated the pace of discovery, but also democratized the scientific process, making it more accessible to anyone with an interest in space. The Pioneer Anomaly became a rallying point for this global community, proving that curiosity knows no boundaries. Perhaps the most inspiring aspect of this collaboration was how it showcased the power of collective effort. While individual contributions might have seemed small, together they formed a mosaic of insights that enriched our understanding of the anomaly. Citizen scientists reminded us that every observation, no matter how humble, has the potential to contribute to something greater. Their involvement also highlighted the importance of fostering a culture of curiosity and lifelong learning, encouraging people of all backgrounds to engage with the wonders of the universe. As we reflect on the role of citizen scientists in solving the Pioneer Anomaly, it's clear that their contributions went beyond data and theories. They embodied the spirit of exploration and the belief that science belongs to everyone. Their story serves as a powerful reminder that the pursuit of knowledge is a shared journey, one that unites us in our quest to understand the mysteries of the cosmos. And as we look to the future, their example inspires us to continue pushing the boundaries of what we know together. Now, let's take a step back and consider how the Pioneer Anomaly ties into one of the most profound questions humanity has ever asked. Are we alone in the universe? While the anomaly itself was a puzzle about spacecraft behavior, it also opened the door to broader discussions about the nature of the cosmos and the possibility of life beyond Earth. After all, every unexplained phenomenon in space invites us to wonder what else might be out there that we don't yet understand. The Pioneer Anomaly, with its mysterious deceleration, reminded scientists that even the most carefully planned missions can encounter the unexpected. This unpredictability is a hallmark of space exploration, and it mirrors the challenges we face in the search for extraterrestrial life. Just as the anomaly forced researchers to question their assumptions about physics, the search for life beyond Earth requires us to rethink what we know about biology, chemistry, and the conditions necessary for life to thrive. Could there be forces or phenomena in the universe that we haven't yet discovered, ones that might influence not just spacecraft, but also the potential for life on distant worlds? One intriguing possibility is that the anomaly could be linked to the presence of dark matter, a mysterious substance that makes up a significant portion of the universe's mass. While dark matter remains invisible to us, its gravitational effects could shape the behavior of celestial objects, and perhaps even create environments where life could emerge in ways we can't yet imagine. If dark matter played a role in the Pioneer Anomaly, could it also be a key to understanding the distribution of life in the cosmos? This idea sparks the imagination, suggesting that the universe might be far more complex and interconnected than we realize. The search for extraterrestrial life also benefits from the lessons learned during the investigation of the Pioneer Anomaly. The anomaly taught scientists the importance of questioning assumptions, revisiting old data, and embracing collaboration. These same principles are essential in the hunt for life beyond Earth. Whether we're analyzing distant exoplanets, listening for signals from intelligent civilizations, or studying extremophiles on Earth to understand the limits of life. The spirit of curiosity and perseverance that drove the Pioneer investigation continues to guide us. And let's not forget the role of technology. Just as advancements in computing and data analysis helped solve the Pioneer Anomaly, they are now enabling us to explore the universe in unprecedented ways. Telescopes like the James Webb Space Telescope are peering into the atmospheres of distant planets, searching for signs of water, oxygen, and other markers of habitability. Meanwhile, projects like SETI are scanning the skies for signals that might indicate the presence of intelligent life. The tools we've developed to study the anomaly are part of a larger toolkit that's helping us answer one of humanity's oldest questions. Ultimately, the Pioneer Anomaly serves as a reminder that the universe is full of mysteries waiting to be solved. Each discovery, whether it's about spacecraft behavior or the potential for life on other worlds, brings us closer to understanding our place in the cosmos. As we continue to explore, we're not just searching for answers, we're also learning to ask better questions. And who knows, the next great discovery might come from an unexpected anomaly, a curious observation, or a moment of inspiration that changes everything we thought we knew about the universe. Now, let's turn our attention to the people behind the Pioneer missions, the scientists and engineers whose dedication and passion made these groundbreaking journeys possible. These individuals weren't just solving equations or building spacecraft. They were driven by a shared dream of exploring the unknown and pushing the boundaries of human knowledge. Their stories remind us that behind every scientific discovery lies a team of curious, determined minds working tirelessly to unravel the mysteries of the universe. Take, for example, the engineers who designed the Pioneer spacecraft. They faced countless challenges, from ensuring the craft could withstand the harsh conditions of space to creating systems that could operate flawlessly for decades. One of the most remarkable aspects of their work was the sheer precision required. Every component, from the antennas to the power systems, had to function perfectly, even millions of miles from Earth. And yet, despite the immense pressure, these engineers approached their work with a sense of wonder and excitement, knowing they were building something that would venture into uncharted territory. Then there were the scientists who analyzed the data streaming back from the spacecraft. For years, they pored over numbers, graphs, and signals, searching for patterns and anomalies. The discovery of the Pioneer Anomaly was a testament to their meticulous attention to detail. It wasn't just about crunching numbers, it was about asking the right questions and being willing to challenge established theories. Many of these scientists spent their entire careers studying the data, driven by a deep curiosity about the universe and a desire to uncover its secrets. One particularly inspiring story comes from a team of researchers who worked on the thermal radiation hypothesis. They spent years running simulations, testing models, and debating ideas, all in an effort to explain the anomaly. Their collaboration was a perfect example of how science thrives on teamwork and shared curiosity. Even when faced with setbacks, they remained committed to finding the truth, driven by the belief that every mystery, no matter how small, could lead to a greater understanding of the cosmos. The human element of the Pioneer missions also highlights the emotional side of exploration. For many of the scientists and engineers, these missions weren't just jobs, they were lifelong passions. They celebrated every milestone, from the launch of the spacecraft to the receipt of the first signals from deep space. And when the anomaly was finally explained, it wasn't just a scientific victory, it was a personal triumph for everyone involved. These stories remind us that space exploration is as much about people as it is about technology. It's about the individuals who dedicate their lives to asking big questions and seeking answers, even when the path is uncertain. Their passion and perseverance continue to inspire new generations of explorers, proving that the spirit of curiosity and discovery is alive and well. As we look to the future of space exploration, we carry with us the legacy of those who came before, the pioneers who dared to dream of reaching the stars. The Pioneer Anomaly didn't just challenge our understanding of spacecraft behavior, it sparked a wave of new questions and ideas in the field of astrophysics. This unexpected phenomenon forced scientists to rethink some of the fundamental principles that govern how objects move through space. It was a reminder that even the most well-established theories can be tested and refined when new data comes to light. One of the most significant impacts of the anomaly was the way it encouraged researchers to explore alternative explanations for gravitational forces. For decades, scientists had relied on Einstein's theory of relativity to explain the motion of celestial bodies, but the Pioneer Anomaly suggested that there might be more to the story. Could there be unknown forces at play, or perhaps even flaws in our current understanding of gravity? This question led to a surge of interest in modified theories of gravity, with researchers proposing new models to account for the spacecraft's unexpected behavior. While many of these ideas were eventually ruled out, they opened up new avenues for exploration and debate within the scientific community. The anomaly also highlighted the importance of precision in astrophysical measurements. Before the Pioneer missions, it was rare for scientists to detect such subtle deviations in the motion of spacecraft, but the anomaly showed that even the tiniest discrepancies could hold valuable clues about the universe. This realization spurred advancements in technology and data analysis techniques, enabling researchers to measure the movements of objects in space with unprecedented accuracy. Today, these tools are used to study everything from the orbits of distant planets to the behavior of galaxies, all thanks to the lessons learned from the Pioneer Anomaly. Another lasting impact of the anomaly was its role in inspiring interdisciplinary collaboration. Solving the mystery required expertise from a wide range of fields, including physics, engineering, and computer science. This cross-pollination of ideas not only helped crack the case, but also set a precedent for future scientific endeavors. Today, many of the most exciting discoveries in astrophysics come from teams that bring together diverse perspectives and skill sets, a trend that can be traced back to the collaborative efforts sparked by the Pioneer Anomaly. Perhaps most importantly, the anomaly reminded us that science is a process of constant discovery. It showed that even the most puzzling mysteries can lead to breakthroughs when approached with curiosity and determination. The lessons learned from the Pioneer Anomaly continue to shape the way we explore the cosmos, inspiring new generations of scientists to ask bold questions and seek answers that push the boundaries of our understanding. As we look to the future of astrophysics, the legacy of the Pioneer missions serves as a powerful reminder that every anomaly, no matter how small, has the potential to change the way we see the universe. As we delve deeper into the story of the Pioneer Anomaly, it's impossible to overlook the pivotal role that technology played in unraveling this cosmic mystery. Without the tools and techniques developed over decades, the anomaly might have remained just that, an unsolved puzzle drifting in the vastness of space. But thanks to advancements in technology, scientists were able to turn confusion into clarity and uncertainty into understanding. One of the most critical breakthroughs came in the realm of data analysis. When the anomaly was first detected, the data from the Pioneer spacecraft was sparse and difficult to interpret. But as computing power grew, so did the ability to process and analyze this information with greater precision. Researchers developed sophisticated algorithms to sift through the noise and extract meaningful patterns from the spacecraft's trajectory. These tools allowed them to identify the subtle deceleration that had initially gone unnoticed, setting the stage for further investigation. Simulation tools also played a key role in solving the mystery. By creating detailed computer models of the spacecraft and its environment, scientists could test various hypotheses in a virtual setting. These simulations helped them rule out some explanations, like gravitational influences from unknown celestial bodies, while pointing toward others, such as the thermal radiation hypothesis. The ability to recreate the spacecraft's journey in such detail was a game changer, providing insights that would have been impossible to achieve through observation alone. Another technological leap came in the form of improved communication and tracking systems. As the Pioneer spacecraft ventured farther from Earth, maintaining contact became increasingly challenging. But advancements in radio technology and signal processing allowed scientists to receive and interpret data from billions of miles away. This not only helped them monitor the spacecraft's movements more accurately, but also ensured that every piece of information, no matter how small, could be used to piece together the puzzle. Perhaps the most remarkable aspect of this technological journey was how it showcased the power of collaboration between different fields. Engineers, physicists, and computer scientists worked together to develop the tools needed to solve the anomaly. This interdisciplinary approach not only accelerated progress, but also set a precedent for future scientific endeavors. Today, many of the technologies developed during the investigation of the Pioneer Anomaly are used in other areas of space exploration, from studying distant galaxies to planning missions to other planets. The story of the Pioneer Anomaly is a testament to the transformative power of technology. It reminds us that solving the mysteries of the universe often requires more than just brilliant minds. It demands the right tools and the willingness to push the boundaries of what's possible. As we continue to explore the cosmos, the lessons learned from this anomaly will undoubtedly guide us, ensuring that we're equipped to tackle whatever challenges lie ahead. Now, let's shift our focus to how the Pioneer Anomaly has become more than just a scientific mystery. It's also a powerful teaching tool. In classrooms and lecture halls around the world, this intriguing phenomenon is used to spark curiosity and deepen understanding of physics, space exploration, and the scientific method. By studying the anomaly, students get a first-hand look at how real-world science works, from forming hypotheses to testing theories and interpreting data. One of the key lessons the Pioneer Anomaly teaches is the importance of questioning assumptions. When the spacecraft's unexpected behavior was first observed, scientists had to challenge their existing knowledge and consider possibilities they hadn't previously imagined. This process mirrors what students experience when they tackle complex problems in physics or astronomy. By examining the anomaly, they learn that science isn't about having all the answers right away. It's about asking the right questions and being open to new ideas. The anomaly also provides a practical example of how the scientific method is applied in real-world scenarios. Students can follow the steps scientists took to investigate the mystery, from gathering data to developing and testing hypotheses. They see how researchers used computer simulations, mathematical models, and advanced technology to narrow down the possible explanations. This hands-on approach helps demystify the scientific process, showing students that it's not just a series of steps in a textbook, but a dynamic, iterative journey of discovery. Another valuable aspect of using the Pioneer Anomaly as a teaching tool is its interdisciplinary nature. The investigation involved physics, engineering, computer science, and even a bit of creativity. This makes it an excellent case study for showing how different fields of study can come together to solve complex problems. For students interested in space exploration, it highlights the collaborative effort required to push the boundaries of human knowledge, inspiring them to think beyond traditional academic silos. Beyond the technical lessons, the anomaly also teaches resilience and perseverance. Students learn that scientific breakthroughs often come after years of trial and error, and that setbacks are a natural part of the process. The story of the Pioneer Anomaly reminds them that even the most puzzling mysteries can be solved with patience, teamwork, and a willingness to keep exploring. As we look to the future, the Pioneer Anomaly continues to inspire the next generation of scientists and engineers. By using this fascinating chapter in space exploration as a teaching tool, educators are not only helping students understand the universe, but also equipping them with the skills and mindset needed to tackle the challenges of tomorrow. And who knows, perhaps one of those students will one day solve the next great cosmic mystery. Now, stepping back to see the bigger picture, the Pioneer Anomaly isn't just a story about a spacecraft behaving strangely. It's a testament to the enduring spirit of scientific inquiry. This mystery reminds us that the pursuit of knowledge is driven by curiosity, the kind that pushes us to ask questions, even when the answers seem out of reach. It's this same curiosity that has fueled humanity's greatest discoveries, from understanding the laws of gravity to mapping the farthest reaches of our solar system. The anomaly serves as a powerful reminder that the universe is full of surprises, and it's our job to keep exploring, no matter how perplexing the challenges may seem. But curiosity alone isn't enough. The story of the Pioneer Anomaly also highlights the importance of perseverance. Solving this mystery took decades of effort, with scientists revisiting old data, running countless simulations, and testing one hypothesis after another. It's a vivid example of how progress in science often requires patience and determination. For every breakthrough, there are countless moments of doubt and frustration, but it's the willingness to keep going that ultimately leads to understanding. This lesson resonates far beyond the realm of space exploration, reminding us that persistence is key to overcoming obstacles in any field. Collaboration is another critical theme woven into the fabric of this story. The investigation into the Pioneer Anomaly brought together experts from diverse disciplines: physicists, engineers, computer scientists, and more. Each brought their unique perspective to the table, contributing to a collective effort that no single individual could have achieved alone. This collaborative spirit is at the heart of modern science, where the most complex problems often require a team approach. It's a model that extends to other areas of life, showing us that working together can lead to solutions that might otherwise remain out of reach. At its core, the Pioneer Anomaly is a story about the human drive to understand the unknown. It's a reminder that science isn't just about finding answers. It's about embracing the journey of discovery with all its twists and turns. This anomaly has taught us to question our assumptions, to persist in the face of uncertainty, and to value the power of teamwork. These lessons aren't just relevant to scientists. They're universal principles that can inspire anyone facing a challenge, whether in their career, education, or personal life. As we reflect on the legacy of the Pioneer Anomaly, it's clear that its impact goes far beyond the realm of astrophysics. It's a story that speaks to the very essence of what it means to be human, to wonder, to explore, and to never stop seeking answers. And as we continue to push the boundaries of our understanding, we carry forward the lessons learned from this remarkable chapter in space exploration, ready to tackle the next great mystery that awaits us. As we bring this exploration of the Pioneer Anomaly to a close, it's worth reflecting on the incredible journey that unfolded over decades. What began as a puzzling deviation in the trajectory of two spacecraft became a profound lesson in the power of curiosity, collaboration, and perseverance. The mystery of the Pioneer Anomaly wasn't just a scientific challenge. It was a reminder that the universe is full of surprises, waiting to be uncovered by those willing to ask questions and seek answers. The story of the anomaly teaches us that science is not a straight path, but a winding road filled with unexpected turns. It shows us the importance of revisiting old data with fresh eyes, of questioning assumptions, and of embracing the unknown. The resolution of the anomaly, rooted in the subtle effects of thermal radiation, underscores how even the smallest details can hold the key to solving the biggest mysteries. It's a testament to the meticulous nature of scientific inquiry and the patience required to uncover the truth. Beyond the science, the Pioneer Anomaly leaves us with a deeper appreciation for the human spirit of exploration. It reminds us that every mystery, no matter how daunting, is an opportunity to learn and grow. The lessons from this anomaly, curiosity, persistence, and teamwork, are not just for scientists, but for anyone striving to overcome challenges in their own lives. They inspire us to keep pushing boundaries, to stay curious, and to never stop seeking answers. As we look to the future, the Pioneer Anomaly serves as a beacon, encouraging us to continue exploring the vast unknowns of the universe. It's a call to action for the next generation of scientists, engineers, and dreamers to take up the mantle of discovery. The mysteries of space are far from solved, and each one holds the potential to transform our understanding of the cosmos and our place within it. So, as we conclude this chapter, let's carry forward the spirit of the Pioneer missions. Let's stay curious, keep asking questions, and embrace the challenges that come with exploring the unknown. The universe is waiting, and its secrets are ours to uncover. If you enjoyed this journey through the mysteries of space, don't forget to subscribe, hit the like button, and ring the notification bell to stay updated on more fascinating stories from the cosmos. Together, let's keep exploring the wonders of the universe.